Okay, so we're going to do another day of the PLC theory, and specifically, we're going to look at the things that you're going to see and hopefully learn in the lab. So this recording today will be a good reference for us to use going forward. So this is the PLC Class 2 recording. So what I'm going to do is we're going to open up our lesson 2. I'm going to share screen here. All right. Lesson 2. So here's what we're going to look at. Opening a file, creating a project, configuring the hardware. So that's the first thing we're going to look at. It wouldn't hurt if you grabbed a piece of paper and a pen and mark down the steps. You can use that as a guide tomorrow, or you could simply open this up and review the steps as you're doing it. So the first thing we're going to want to do is open a file and create a project and configure the hardware. So we're talking about RS Studio. We looked at this last day, but after you get into our lab through workspace.bcit.ca, you're going to have a virtual computer you're operating on in either room 116 or 210. And it's going to have this software here in this desktop specifically. So open a file, create a project. That's going to be Studio 5000. So if we double click on Studio 5000, it's going to give us the options to create, open, explore. We want to create. We're going to create a new project. So we're going to create a new project. And we'll choose Logics. So the first step of creating a new project is we have to choose the processor that we're using. And the processor that we're using is the 5570 controller series. And more specifically, it's a 1756L71. How would you know that you have a 1756L71? The only way you would know that is if you were actually physically looking at the processor itself. And it will say on it, Logix 5571. So that's the 55 series and the 71. So there's the processor we have. We're going to give it a name. We'll call it example. Choose next. Now this next screen will bring you to some options like revisions. This is the software revision that we have. We have revision 32. You can see here there are no other choices. So we've removed every other choice for you. This is the most current revision of Studio 5000, or it was 10 weeks ago now, but I'm pretty sure it's still the most current revision. That's revision 32. The next thing is chassis. That describes the rack or the backplane. So this is how many slots the rack is. And the only way you would know that is if you were here in the lab and you could count them. So we have a 13 slot rack, but you don't have to define every slot if you're not going to be using it. So we only use 7 or 8 slots. So we could leave it as a 10 slot rack, or we could actually go configure it for what it is. It's a 13 slot rack. Now with control Logix, which is different than compact Logix, it gives you the option to install your processor in a different slot other than slot 0. And the reason for that is you could have multiple processors on one rack or in one backplane if speed was a concern. So you could subdivide what the tasks are depending on the processor to help speed up your process. So our processor is in slot 0, so we're going to leave that, and we're going to hit finish. Once we hit finish, then the project will open up, And on the left-hand side of the project should be the name that we gave it, which was example. And then what you're going to do is take notice of your controller organizer. Do we need Studio 5000 RS Studios on our own computers? The answer to that is no. You're going to use our computers here in the lab that already have Studio 5000 on it. Okay, so now Studio 5000 has opened. I'm going to maximize this so it's a little bit easier to see. Right down here, under where it says I/O configuration, you'll see backplane 1756, 1756 A13. A13 describes how many slots you have in that particular rack. We have 13. 1756 L71 example. So 0 is in slot 0 is your processor, which is a 1756 L71. And we've named this particular project example. So with the older versions of RS Studio and the older versions of RS Logix, it would be necessary to pull the IP address to get the information which is on the backplane. So for example, if I just simply open up a browser and I type in 142.232.195.100. That's the IP address of the PLC that I'm looking at right above my head. This should open up. I could see all the modules that are on that particular rack and the revision numbers associated with it. Okay, so that's the old way of doing it. I would have to pull the IP address and then write down everything I have and where it is. So in slot 0, that's my processor, slot 1, output module, slot 2, input module, and so on and so forth. I don't have to do that anymore. I don't have to do that. This has a neat way of discovering the modules. So if I were to go up here to communication and who's active, I can actually go online with my controller. So I go Ethernet IP, I expand that. These are all the PLCs that are there. I'm going to choose 100. That's the one that's closest to me. Physically, I'm sitting here in the lab 116. So I highlight the processor, and now when I hit download, I'm essentially downloading nothing to the controller because I didn't put in any program. But what I do accomplish from this is I make a connection to that backplane, and now I can discover all of the modules, and I can ensure that I get the firmware right, I got the slot right, and I'm able to install everything. So now that I'm online, I can see up here in the green, it says run mode and controller OK. If I right click on the backplane, I can hit discover modules. And I can see all of the modules that are connected to that backplane. I could simply hit create, and that would install the modules. But before I do that, I want to show you something under controller tags. Okay, so see how there's nothing there under controller tags? Here is the idea. When we install a module, I'm going to discover modules. Then I'm going to install my output module. Now I could give it a name, or I could just hit simply OK. It automatically picks the right revision. I hit OK, and it installed the module. Now when it installs that module, it automatically allocates memory for that particular module. I'm going to install the input module as well. Okay, so I've installed 1756 OW16I, 1756 IB16. So 1 tells me that we're in slot 1, O tells me we're in output. If you were to Google this and download the data sheet, it gives you all the specifics of that particular output module. And the same for the input module. So we automatically have allocated memory for this output module. Now, does anybody remember from Friday what local means? So I see local :1:O dot data. So this is one of the test questions. Local, perfect. It's in the same chassis. It's being the processor. It means the processor and the output module are in the same chassis. One refers to the fill in the blank slot. Yeah. O is output. And then data refers to all of the registers that are associated with that particular output module. And it defaults to 32, which is a data type of double integer. Okay, we're going to talk about that a little bit later. But the idea here, these are registers. So tomorrow in digital logic, we're going to be looking at something called flip-flops. And what those are is registers. And the idea behind a register is it's a part of memory which houses a bit. And in this case here, we're housing 32 bits of information. 16 of those bits we're not even looking at, because I know from looking at the data sheet that the output module has 16 outputs, so I'm only interested in the least significant 16 bits. So I have 4, 8, 12, 16. That's those first, if you read it from right to left, that's those first 16 registers. And that is the outputs. The inputs are right here, local :2:I dot data dot, and then something else. So local says that our processor and our input module are on the same register. 2 says we're in slot 2. I stands for input. Data describes all of the possible inputs. With now when I look at the data sheet, I realize, well, I only have 16 inputs, so the first 16 are masked, which means you don't see them, and we only see the second if I'm reading this way. So this is the least significant bit. That would be input 1 or input 0 in for Alan Bradley. Alan Bradley starts his count at 0, but regardless of that, it's the first input. Then I would count all the way to 16, and that would be input 15, of course, with 16 inputs starting at 0. Okay, so that is the first part of this. So that is creating a project and configuring the hardware. Creating a project and configuring the hardware. So it's going to ask you to do that tomorrow in the lab. It's going to ask you to create a project and configure the hardware, and it walks you through it in the lab word for word. But it's much nicer if you have something to refer to, like a little video, which is what this is right now. So that's creating a project, configuring the hardware, configuring the rack. All right, creating tags. Base tags, alias tags, controller tags, program tags. Let's see what our notes has to say about that. Creating a tag. A tag lets you allocate and reference data stored in the controller. A tag can be a simple single element, an array, or a structure. There are 4 types of tags that you can create. Those 4 types are base, alias, produced, and consumed. And we'll talk about, we're going to be interested in 2 of those. Produced and consumed, I might have even deleted out of here. Yeah, I did delete out produced and consumed. So all we're interested for with regards to this level of PLCs are base and alias. Base refers to a normal tag selected by default. This type of tag allows you to create your own internal storage. Base can be thought of as internal. Alias allows you to assign your own name to an existing tag. Alias can be thought of as external. So let's talk about the first 2 parts here, base tags and alias tags, and what they are. Let's go back and look at our program or our project rather. Okay, so I'm going to go up here. I'm going to create a program. Okay, so this is an examine on instruction, also known as X, what? XIC, yeah. Okay, and what does the XIC instruction like to see for that instruction to be true? Does it want to see a 1 or a 0? 0 equals true. Are we sure about that one? 1, yes. So this instruction here wants to see a 1 for that instruction to be true. Now watch what I'm going to do here. I'm going to assign this to an input, and I'll assign the output instruction to an output. Your notes are wrong then. All right, so all right. This is an input tag. By definition, let's go read it. A tag lets you allocate and reference data stored in the controller. All right. So when we installed this module, 1756 IB16, we automatically created these tags. The memory locations were automatically allocated for them. So that's looking at input 4, local :2.I.data.4. That's input 4, and there's a place in memory for that. If I go to controller tags, there's input 4 right there, and I can see it's a 0 right now. Okay, so there's a spot in memory that's going to house a 0 or a 1 for that input. Local :1:0.data.1. There's a spot in memory that's going to house a 0 or a 1 associated with that output. So if I go to controller tags, I minimize that and I look at that. Local, which was it? 1. So local :1:0.data.1. There's a spot in memory which houses a 0 or a 1 associated with that output. Okay, so that's a tag. Now here is an alias tag. I'm going to create an alias tag. I'm going to say limit switch. Okay. So what I did is I created 2 additional tags. The first tag I created was called limit_SW, and I assigned it to input 2, local :2.I.data.2. I assigned that to input 2. And then the second tag I created was pump coil, and I assigned that to local :1:0.data.6. So the first limit switch was assigned to input 2, and the coil was assigned to output 6. Now up here, I didn't assign any tag name that referenced that input, and I didn't assign any tag name that references that output. But now when I choose limit switch, I can see that limit switch is the identifier that references that particular spot in memory. And the same can be said for pump coil. So the reason for this is when you're writing a program or when you're reading a program, if you're a maintenance electrician, you want to be able to go to the screen and have simple identifiers which reference the inputs and outputs that are meaningful. If you went to the computer and you just seen local :2:I.data.4, yeah, you could put it together that this is referring to input 4, but you don't really know what that thing is or what it's supposed to be without cross-referencing it with some sort of data sheet. Whereas if you look at the second one, you can see, limit SW. That's probably a limit switch wired to input 2. And this is probably a pump coil wired to output 6. And that is referred to as an alias tag. Alias tag allows you to assign your own name to an existing tag. So when we installed those input and output modules, they became existing tags. And when we created that name and referenced those existing tags, we created our own alias tag. Alias can be thought of as external. And what that means is you're referencing something that's external, like an input or an output. A base tag refers to a normal tag selected by default. This type of tag allows you to create your own internal data storage. Base can be thought of as internal. So what that means is this. You can think of it almost like a relay where you're turning on something else. So if I want to create a base tag, I go here, I hit edit tags, and I'm going to call it something arbitrary. I'll call it pencil. Just to show you that it's just a name to represent a spot in memory. Okay, so this word pencil is going to reference a spot in memory. And if by default, if I don't choose a data type and I just hit enter, it's going to create 32 spots in memory. But if I assign it a data type, then it just assigns it 1 bit. So what I did is I created an internal bit called pencil that's assigned to 1 bit. Now, if I go back here, I can create the same, basically the same program, limit switch. So the idea here is, let's say that limit switch is wired normally closed. This would be a good test question. If the limit switch was wired normally closed, and I don't trip the limit switch, the coil is on or the coil is off, according to what I have here. Is there anybody still with me? Yes, that's right, on. So a base tag does not physically exist. Yes, that's right. It's only local to the computer itself, to the controller. Yeah. Things like timers, those would be base tags. They exist only in the controller. Latches, one-shots, math functions, internal bits like I've created here. These are all base tags, which means they don't exist on the outside world. They only exist within the parameters of the controller itself.
You are now muted.
Okay. All right, so let's go back to our notes here. So that's base and alias. So it's good to use word association. Base can be thought of as internal. Alias can be thought of as external. So base would be things like timers, counters, latches, one-shots, internal bits. And alias would be inputs and outputs. Okay, so that's the difference between the two tags. Alias, inputs and outputs, base, everything else. Controller tags and program tags. Program tags are now called parameters and local tags. Controller tags can be thought of as global, and they actually changed the name. These used to be called program tags. Now they call them local tags. When we do our labs tomorrow, all tags must be created under controller tags. Don't create any tags under parameter or local tags. We want them all to be global. So for factory IO to work, you must create all tags under controller tags. Controller tags are global. Local tags are local. Well, what does that mean? We have one main routine here. That's it. One main routine. It is possible to have what's called subroutines. So you have one main program, and inside your main program, you call another program. So let's say, for example, you have a process that has a manual and an automatic state. Your process has a manual state and it has an automatic state. You might create a program, a main program, which simply is 2 lines. If your selector switch is here, jump to the automatic program. If your selector switch is there, then jump to the manual program. Those are called subroutines. So your main program just tells you where to go, and it's generally used to organize your process well for readability. So it's easier for a maintenance person to come and look at it and understand how this thing works. Now, the idea behind that is this. You might have multiple stop buttons. You could have a stop button. Maybe you have a main routine, which has 3 different processes. Each one of those processes is a subroutine. Each one of those subroutines have stop buttons. Well, you could reuse the name stop button if you created it local to the routine. But if you create a tag up here called limit switch, right there, limit_SW, I can never create that tag anywhere else. In fact, if I went to local tags and I tried to create the tag limit switch, I made that a bool. It says controller scope tag limit switch already exists and it is referenced by a routine within a program of the main program. Okay, so it does allow you to do it, but it's called what's called a duplicate destructive bit. And you would never do this. There is no reason I could ever think of that that you would do something like this. Yeah, in fact, when you try to verify this, it should say that you've got a problem with your routine. Okay, so the idea behind that is all the tags we're going to create them under controller tags. And they all have to have a different name. You can't recycle names because your controller won't know which one you're trying to reference. And the only time you can recycle names, and it's not even a good idea to do it then generally, is under program or local tags. So if I had 5 subroutines and each subroutine had a stop button and they're different stop buttons, I could reuse that word stop button. But I've spoken with a lot of consultants, and they generally stay away from this. That way you don't get mixed up on what you're looking at. If you see the word stop button, it should only reference one thing, and you know where it is and what it is. So you might call it stop button 1, stop button 2, or stop button and then reference the machine it's stopping, something like that. Data types. So tomorrow we're going to look at registers, and registers and digital logic, and registers store information, and data types tell you how much information you're storing. If I create a tag, I'll call it stop button. And if I reference an input, it's automatically going to kick that data type to a bool, which is 1 bit. But if I don't reference anything, it defaults to a double integer, which means this. I just created 32 stop buttons. So when I stop light, so if I create 2 tags, stop button and stop light, and then I go try to set them in here on this program, it shows an X in this corner. This X is telling us there's a syntax error with this program. And if I hit the verify routine, it gives me 2 errors. It says the operand has an invalid data type. The argument must match the parameter data type. And what that means is this. This is an examine on instruction, XIC, examine on instruction. And there's only 2 possibilities that can be. It can be a 0, it can be a 1. But you've given it 32 possibilities. So if I typed in here .8, then that would be fine. And if I typed in here .9, then my error would go away because I'm only referencing 1 bit. So the data types that we're responsible for are, should put down here to timer and counter. Those are 2 data types that you're also going to be responsible for. So you have bool, sint, int, and dint. Bool is 1 bit. Int is 16 bits. Sint is half that. Dint is double that. So we have bool, which is 1 bit. Sint is 8. Int is 16. Dint is 32. And that used to be referred to as word and double word, but they've consolidated with an IEC standard and call it now integer and double integer. So how many bits is a sint? 8. Int 16. Dint 32. I think what I'm going to do now is I'm going to break us into groups for 15 minutes. And I want to walk everybody through on how to log in to our sections. Okay, so to our labs. So here is how you log into our lab. You open up a browser. You type in workspace. .bcit.ca. That'll bring up this screen here. You're going to log in with your student number. You're going to choose desktop. And now you're going to pick a lab to go into. So here is what I'm going to do. I'm going to break us into, let's say, 8 groups. And this should only take no longer than 15 minutes, and then we'll go for coffee. I just want to make sure everybody can log into our computer room. And then what I'm going to do is I'm going to define the IP addresses for the groups. Back here. Okay, so you can mark this down as I'm typing it out. Group 1. Group 2. Oops, that should say 120. You see it in the notes. Group 3, 130. Group 4, 40. Group 5, 50. 6, 160. Let's just go with 6 groups for now. Okay, so these are the IP addresses for the groups. You'll notice that I left group 110. I've left that alone because that's the one that I'll always be referencing. I'll always reference PLC 110. So the IP address is this: 142.232.195. So for example, group 1, it'll be 142.232.195, 100. Group 2 will be 142.232.195, 120. Group 3, 142.232.195, 130, and so on and so forth. So I see some comments here that you don't see anything. It's in the public chat is where you should be looking. So I've assigned the groups IP addresses in the public chat. So group 1, 142.232.195, 100. Group 3, and so on and so forth. So you don't know what group you're in yet. So here's what we're going to do. I'm going to break us off into groups. I'm only going to create these groups are only going to last for 15 minutes. Maybe I'll do 20 minutes. I'll do 20 minutes. And what I want each group to do. Now you don't have to do this individually. You can do it just as one group. And one person who's driving the bus can walk everybody through it, or you could do it individually in your groups. But bear in mind this. Let's say I have 6 people in group 1. 6 people cannot go onto that PLC. Only one person can go on it. So if everybody wants to VPN into our classroom, just to make sure you know how to do it, that would be a good idea. But only one person in the group can actually communicate with the PLC. Okay, so I'm going to break us into the groups for 20 minutes, and then we'll do that. Yeah, you have to have Citrix. Okay. Okay, there we go.
You are currently the only person in this conference.
Oh boy.
Hello.
Hey.
Sorry, I had my mic on. I didn't know when it turned on.
No worries. So I already have it open here, workspace. I mean, where do we enter the address? I don't even know.
So
Uh,
workspace. What do you mean you can't enter it?
uh-oh.
Oh. Try again.
There you go.
What happened to this? It was working earlier.
I wonder if it's because every workspace has been logged in or something.
Oh, there you go.
Oh, there you go.
Yeah, so you go to desktop.
Yeah, I got my Studio 5000 opened up. Oh.
He only wants us to log in as far as here, right?
Right, is that it?
Yeah.
Oh.
And then Studio 5000.
Yeah. No, he gave us those addresses. Like, where do we enter those for the PLCs?
I guess it's new. Which one was he using before?
The 71, yeah. No. Uh-oh. Yeah, so I have that open, but like now what?
Said under controller tags, right?
But he was doing a lot of stuff on the controller tags, sure. What?
Trying to see if there's any instructions on this thing that he gave us.
Oh, the lab file?
Maybe the lab file will have something.
Yeah, there's a lab file called Create a New Studio 5000 Project.
Alright, let's see.
Open RS links. What? How?
I'll pull this right here.
Oh no. That doesn't look like what we have.
No, it doesn't. What is this RS link?
Keep going, keep going.
This is the thing that he was using, but we don't have this, do we? Let's see.
No.
RS link. Oh, this thing.
So from uploads. Huh. Oh shit.
So from here, click communications. Configure the drivers.
No. What did I do?
Available drivers. Select Ethernet port. Ethernet device.
Oh, okay. So we gotta do all that. Okay.
Yeah.
RS link. Oh boy. Okay.
Add new.
Communications. Configure drivers. Ethernet.
That does not look like what he has here.
Oh.
Right.
AB is running. Okay.
Yes, this one.
Should be running.
Okay, now it shows running.
Okay. No close, so no RS who.
The heck is this RS who?
Okay, so is that why
RS
where
who?
we find our
So
freaking
communications and then RS who.
RS who?
And now you should see all Ethernet devices on the local network.
What do you see?
So
Yes, that's what I
we
see.
need. Which one is the right one?
Oh my.
It's one of these two, I think. Right?
Lord, okay. R325哦 no oh right
That's a lot.
I guess we're supposed to find the one with address 192.192.195 something like that. I
It was
think I found
142.232, and then what
195.
group number are we?
We are number 2.
Number 2.
Group
So
2, yeah. So 120.
120. So it should be this one.
Okay, that's what I see. Okay, good. We're at
Yeah.
the same place.
So
So now what?
uh,
Oh, fuck. We're team 2. What?
device properties.
Oh.
Or the device number. Device number.
Oh.
That's the wrong one.
We found that. Lock 0. Device properties.
Is it that? Which one's the device number?
Record the device name and number. Okay. Repeat for all the mod. Oh my god. Okay.
Hey, wasn't he saying that only one of us can do this? Or are we all supposed to be doing this right now?
I think only one of us could connect to it at once.
Yeah, but we can probably see the properties and such all together. But when it comes to actually using it, only one of us can connect to it, I think.
Yeah.
So who's connected to it now?
I think both me and Gabriella are
Yeah.
connected to it, but
I'm
none of
connected
us
to
are
it.
actually using it. We're just looking at the numbers and stuff.
Oh, okay. I just got to the point where I opened up Studio 5000, so I'm like,
Oh,
wow.
okay.
No worries.
We're not even using the Studio 5000 right now. We're using RS links.
Oh, okay, okay.
Yeah. I
He
don't
said
know
we
how.
could do this in 15 minutes? What?
I think he means the 15 minutes is only logging into the computer itself. I don't think it's this part.
I hope so.
Yeah.
Record the device name and revision number. Okay.
Yeah. So
device
slot
name.
1 would be. Of course, this is in protected view.
Oh my god, there's so many numbers. Okay.
So we have to go through like each of these ones
Oh
and
my
record
effing
this device number and revision
logic.
number.
Revision is okay.
I can't even type in this thing.
It's not edible.
No,
Editable.
he put protected view on it.
Ew. Why?
Yeah.
Oh my god, it's
I'll
so
get rid of that when I have time. Yeah, so I think he wants all these ones, all these numbers, one by one.
okay.
And then you.
We're actually doing the lab now, I guess.
This is supposed to be tomorrow.
I guess, yeah. Hey, the protected thing doesn't work on the MacBook pages. That's awesome. Yo.
How much time do we have left?
9 minutes. Uh,
Yeah, I don't think we need 15 minutes to try to log into Workspace. I'm pretty sure everyone else could try logging into Workspace as well, because that one is individual. I think the part where you can only have one person is when you're actually connected to the address itself to control the
I agree.
PLC.
I think so too.
You guys know if this works on a Mac?
I'm
It
doing it
should.
on the Mac right now. Yeah, I'm doing it on the Mac right now.
You could give it a try.
Yeah, I downloaded it, but then I can't start the desktop.
So
You need your browser to start the desktop.
yeah, the app itself doesn't have this tab
Yeah, I'm
right
using
here.
the browser on Google Chrome.
Okay.
Oh,
Huh.
okay.
It's like, can I start desktop, SE, blah, 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 blah.
So you click on this and then you hit open.
Yeah, that's when the error code pops up.
Oh, maybe we can only because we are on it or something. I don't know. I wonder.
I don't think so. I could try logging out of it.
Because if they're computers, I guess only one person can be controlling. I don't know how it works.
Here, I'm out of it, so you
Yeah,
give it a
try
try
again.
now.
Refresh it.
Oh.
Now it sounds like you're driving.
Very windy there.
It's okay, I'll figure it out.
Well, you got 6 minutes to try to log in
Yeah.
before class starts again.
Yeah, try the which one is this? I'm on 0116. So try 114 maybe. Don't try it.
Okay. Yeah, it's cannot start desktop, SE, and blah, blah, blah. 141.
Huh. Okay.
I was getting a lot of that too. I just kept on trying to log in over and over again, and eventually I got it.
Oh, eventually.
There you go. Persistent. Well, maybe because everyone's trying to log in the whole class, so a little low. What?
Is everybody else able to log in?
Oh. So far, so good. Okay, and after we enter all this, we go to Studio Platform. Oh, A. Select.
Oh, I don't think I ever logged out. I just opened it again. It continues where I left off.
What? We're team 2 to place. Oh. Oh. Neat. Huh. Okay. Oh.
Okay, we're going to be kicked out here in a quick second. Were you able to VPN in?
Yeah.
Okay, perfect.
Okay, well, see you guys on the other side.
Yep.
You are now muted.
Hello?
Hello.
Oh.
All right, so we're back. I see from the comments there were all kinds of issues, which I kind of figured there probably would be. So what we're going to do is we're going to try that again towards the end of class, and what we'll do is only those who had issues getting into the system can stick around. So if you're able to VPN in and get into our system, then you won't need to stick around at the end. Just only those who had had problems either with Citrix or VPNing in or anything like that, then stick around. I've set the class until from 11 till 11 to 12, 12 to 1, till 1 o'clock, 1:30, and then we'll break off into the groups and try that again. All right. So here is where we left off with the data types. So bool, sint, int, or dint. Bool, sint, int, or dint.
Please record.
So we left off with our data types, bool, sint, int, or dint. Just as a bit of a review, how many bits is an integer? How many bits is an integer? Does anybody remember? 16, perfect. So that's usually the one, that's the base one that I remember, is integer is 16, and then single integer is half that, double integer is twice of that. So double integer is 32, single integer is 8, and a bool, of course, is 1. Don't be tricked by 2. A bool is not 2 bits, it's 1 bit that has 2 possibilities. So bool is 1 bit. Sint is 8, int 16, dint 32. Timer and counter is your other 2 data types, and we'll look at those when we go over the timer and counter. So what we're going to look at now is a couple new instructions. We're going to look at latches and one-shots. So the latch, when enabled, the latch instruction sets a data bit. The data bit remains set until it is cleared, typically by an unlatch instruction. When disabled, the latch instruction does not change the status of the data bit. So, when I say low voltage release or low voltage protection, what does low voltage release mean? Or what's another way of thinking low voltage release? Yes. Okay, so it's like a holding contact would be, okay, so the holding contact, would that be low voltage release or low voltage protection? Does not energize after a power failure. Yes, exactly. So the idea there is low voltage protection is also known as 3-wire control. And the idea there is the system does not restart after a power failure. Well, this is the opposite of that. A latch is synonymous with 2-wire control. And the idea behind that is that the bit would be true after the power come back on. So a latch can be thought of as 2-wire control or low voltage release. And the idea is that the system would be energized again after a power failure. So let's take a look at that. So to create a latch, we need a minimum of 3 instructions. We need the latch, the unlatch, and the bit we are latching. So up here in the instruction palette, we have examine on, examine off, and our output instructions. Well, beside our output instructions, we have the U instruction and we have the L instruction. The U instruction is the unlatch. The L instruction is the latch. So let me show you how this works. Let's say we have a pump or a fan, typical loads that you would utilize 2-wire control. Power goes out, power comes back on. You don't want to have an operator reset the system. Okay, I'm going to go in and I'm going to create some tags. I'm going to call this on push button. I'm going to assign it to a real input. I'm going to call this off push button. Assign it to a real input as well. I'll say that this is a fan. That can be assigned to a real output. Okay. Now I'm going to create a tag for the latch. Should this be a base tag or should this be an alias tag? And what's the difference? So I'm going to create a tag for the latch. Yes, it should be a base tag because it is, fill in the blank, internal. There, you got it. Okay, so I'm going to create a tag and I'm going to call it, I called the last one pencil. I'm going to call this pen. I'm going to make it a bool. And so I'm going to assign these tags. There's on push button. There's off push button. Okay, this will be my fan. Now the idea here is when I trigger this L, it's going to drive a 1 into one of the tags. And I just so happen to call this tag pen. Now, there's a reason that I'm picking these arbitrary names. Generally, what you want to do is you want to choose meaningful names that represent the functionality of the instruction. But for learning purposes, it gets confusing between the tag name and the functionality of the instruction. And here's why. In the lab, we don't call this pen, we call it latch. Guess what students love to call this? When we create the tag latch, guess what students, yes. But that's what you've done, and when you call this latch and you call this unlatch, is you created two separate, two different things. You created two different things. So that's why I just created the one tag called pen, and it's a bool. So when I download this and run it, so I toggled the bit, and I can see now that this instruction is false, but there's still pen is still equal to 1. So some students may look at this and say, hey, how come the unlatch instruction is true? And it's not that the unlatch instruction is true. It's just showing you that that there's a 1 in pen. So if I go to controller tags and I look at pen, I can see that there's a 1 there. Okay. So how do I, if I were to turn the power off, turn the power back on, I would see this system start back up again. Now to turn this off, I got to, I think I'll force that bit. That way you'll be able to see that when I force this bit, okay, so when I force the off push button, so I'm pushing this button, it drives the unlatch instruction, which sets the bit associated with pen back to 0. Okay, so what's the purpose of this? 2-wire control. if you're gonna, if you want to turn something on, and then the only way you want to turn it off is by hitting this push button. Turning the power off and turning the power on will only have the impact of interrupting the power to that device. Once you turn the power back on, then it'll start again. And that is 2-wire control. So a latch can also be thought of as 2-wire control. Okay, the latch one usually is not much of a problem. It's the one shot which causes some grief. So the note here says, when enabled and the storage bit is cleared, the one-shot instruction enables the remainder of the rung. When disabled or the storage bit is set, the one-shot instruction disables the remainder of the rung. A one-shot instruction will only allow logic past it for one scan, provided the previous instruction is true. Okay. Let's look at an example. Oops. Now, we're not responsible for math functions, but I'm going to show you one to explain how the one-shot works. Okay, so I've created a math function here. The idea, this is an add function. So it says source A, source B, destination. And the idea here is as long as this function block is true, it's going to go A plus B and store it in the destination. So I've just driven two values in here. I said A is equal to 10, B is equal to 5. And every time this function is true, it's going to go 10 plus 5 equals 15. Next scan, 10 plus 5 is 15. Next scan, 10 plus 5 is 15. All right, so I'm going to download and run this just to verify that what I'm saying is true. Okay, so I'm going to force this on. And I'm going to enable forces. Okay, so there, I forced that on. So what this is doing right now is scanning, and it's going 10 plus 5 is 15, 10 plus 5 is 15, 10 plus 5 is 15. And it's doing that thousands of times per second. I'm going to take advantage of this add function and the way that the system scans to solve a problem. Okay, so one of the projects I used to give was a microwave, and every time you hit the button on the microwave, you add 10 seconds to the timer. So the point is here, I would use this button. Every time I press it, I would add 10 seconds to the timer. Then I would use another instruction called a move, and I would move that into a timer. But in any case, we're just going to utilize the scan here. So when I push this button, I want to add 10 seconds to the timer. So if I do something like this, I'm going to drive that to 0, and I'm going to call this drive that to 0. I'm going to go offline here. I'm going to look for answer. Okay, so the way this would work is source A plus source B equals destination. 10 plus 0 equals 10. And then answer would be updated to 10. And then on my next scan, it would go 10 plus 10 equals 20. My next scan, 10 plus 20 equals 30. And the idea being every time I hit this button, I want to add 10 seconds to the timer. So what I'm going to do is I'm going to download this right now. And now I'm going to force this on, and I'm going to force it off as fast as I can. So I'm going to force on. Then I'm going to enable all forces. Yes. And then I'm going to force off. Okay. So I forced it on and off as quick as I could. And how many scans just took place? So I just forced that bit on and off. A lot, yeah, but the exact number of scans. Yeah, I think that's right. Divide that by 10, and we got 70,358 scans just happened because it was adding 10 each time. All right. So now what I'm going to do is I'm going to put in a one-shot. Okay, so I already made the tag pencil, so I don't have to call this one-shot just because it is a one-shot. I just gave it a name. And the idea behind a one-shot is once the instruction is true that precedes it, which in this case is on push button, pencil will be driven to a 1, and then you're going to execute everything else that's on that line. So you're going to go 10 plus 0 equals 10. And then you're going to come back up here, the next scan, and you're going to go, you're already a 1. And so you're going to jump to the next instruction. And this next instruction, they're going to say, oh, this is a one-shot. And it's a 1. So it's going to put up a wall here and block all logic past it. So it's only going to allow this instruction to be executed once, regardless of how long the instruction that precedes it is true. Okay, so now when I force this on, and I enable the forces. All right, so we can see that 10 plus 0 equals 10, and it shuts it down right there. Now, the only way to reset this one shot is I'm going to force this off. When I force that off, it resets the one shot. Now, when I turn it back on again, it allows the this instruction to be actuated again. Okay, so that's the one shot. Oh, let me go back to program mode here, go offline. Okay, so my question here is, Let's see if we have a general understanding of how the scan works. When will any variable, any var, be true? Or will it ever be true? When will any variable be true? Or will it ever be true? How often will it be true? Any variable. Okay, so let's say this is multiple choice. I'm going to put A all the time, B never, C every other scan, D not sure. How many people are going to pick D? Mostly everybody, probably. Okay, so all the time, never, every other scan, not sure. And we have that. Melting in the heat. C, perfect. C is never a bad choice if you're not sure. Okay, so this will be true any other scan, every other scan. Why? Well, take a look. Remember, I don't know if you recall, but what I said on Friday was everything wakes up a 0. So when this thing does its first scan, what happens? Well, any variable is internal and it wakes up a 0. So it's going to be true on the very first scan. So we've got true. Then we jump to the next thing. Okay, well, that's going to take any variable and drive it to a 1. All right. Then we're going to hit the end of line and we're going to do our second scan. Any variable is now a 1. So this is going to be false. If this is false, it makes this false. Okay, next scan. Any variable is a 0, so it's true. If this is true, it makes that true and drives that to a 1. Then we hit the end of line, come back up here again, and we've repeat our cycle. Now that it's a 1, false, false. Next scan, true, true, false, false, so on and so forth. So this, any variable, will be true every other scan. All right. Let's work our way through these last 2 instructions, and then we'll call it a day, and we'll jump back into our groups if we want to figure out how to use Citrix. I'm hoping everybody has air conditioners out there. I just looked at it. It's supposed to be the hottest day ever recorded in Canada. So I understand if people want to hit an air conditioning car and go for a drive if they don't have air conditioner in their home. Okay, so let's look at timers and counters. Yeah, you probably don't want to go for a drive if it's if your air conditioner's broken. I got an electric car, so it's nice. You just plug it in and Don't have to worry about gas. Okay, timers and counters. I think everybody needs an electric car. They're awesome. The TON instruction is a non-retentive timer. When the instruction is enabled, the run condition is true. The TON instruction is a non-retentive timer that accumulates time when the instruction is enabled. Okay. The TOP instruction is a non-retentive timer that accumulates time when the instruction is disabled. The RTO instruction is a retentive timer that behaves like an on-delay timer, TON. Okay, so on-delay timers from second year and third year probably. On-delay timer, when we energize the coil, the contacts will time themselves either closed or open, depending if they're normally open or normally closed. Okay, so that's an on-delay timer. That one is fairly easy to understand. You energize the coil, then the timing action happens, then the contacts change state. It's the off-delay timer that causes all the problems. Off-delay timer works when the coil is de-energized. So the idea is you energize the coil, the contacts change state immediately, and then once the coil is de-energized, the timing action starts. And where students get confused is they say, okay, the off-delay timer, the contacts changed immediately, then the timing action starts. No. The contacts change immediately after the coil is energized, and then they just stay that way until the coil is de-energized. Once the coil is de-energized, then they'll time themselves to their other state. Let's take a look at that. So this is timers. Both on delay and off delay have the following bits associated with them: EN, TT, and DN. EN stands for enable, TT stands for timer timing, DN stands for done. The enable bit will indicates that the timer instruction is enabled. The timing bit indicates the timing operation is in process, and the done bit behaves like the associated hardwired timer. Preset and accumulator. Preset is what you set the timer to be. The accumulator is the current time that the timer is. So let's look at a timer. Timer counter. TON is an on delay. Okay, I'm going to create a timer called Frank. And what's my data type for timer? Does anybody remember? What is the data type for timer? Any guesses? The data type for timer is timer. Okay, so remember that when I ask you what the data type for counter is. It's going to be very similar to what we just looked at. Okay, so timer has, so I created a tag called Frank. I associated it with a timer. And now when I open up the tag Frank, I see preset accumulator. Now the preset is a double integer. The accumulator is a double integer. And now I have EN, TT, and DN, which are all bools. So the EN bit will be true when the timer is initiated. The TT bit will be true when the timer is timing. And the done bit behaves like the contacts do with the associated timer. So when I go back to here, I'm going to look for Frank right there. And I'm going to set the timer for, let's say, 4 seconds. Okay, I set it for 4,000. So what does that indicate that the units of measurements for the timer are? milliseconds. Perfect. Okay, now I want the EN, the TT, and the done bit. Now the way I do that is I go open up Frank, and I choose the right bits. EN. TT. And DN. EN, TT, and DN. I'll make this a new tag, call that red, yellow, and green. All right, so I'm going to download and run this. And my question is going to be, before I close the switch, which lights, if any, are on? Before I close the switch, which lights, if any, are on? None. Perfect. It's not enabled, it's not timing, and it's not done. So I'm going to close the switch and I count to 2. Which lights will be on, if any? Red, yes. Red will be on. What about yellow? Will yellow be on? Yes. And the green, no. Okay, so I'm going to put this in run mode. Okay, so this is timing now, red and yellow. After 5 seconds, and the green light comes on. And the yellow light went out because it's no longer timing. The red light stays on as long as this is true. So when I remove the force, set the force off, then they all go back to their natural state. Okay, that one's pretty straightforward. This one here, change to an off delay. This one here is what causes the confusion. Okay, the off delay. Okay, now when I force that on, which lights, if any, will be on? None. Nope. Some of them will be on, probably. How about the red light? If I make this true, is this function block enabled? Yes, it is. So the red light will be on. Will the timer be timing? It's an off delay timer. Will the timer be timing? No. So the yellow light will be off. And the done bit can be thought of as like the contacts associated with the timer, with the off delay timer. So this done bit will be true. So when I force that on, I should see the red and the green light go on. Red and green on. Okay. When I remove the force, the instant I remove the force, will the red light be on? No. You have to look at the definition. The EN bit will only be true when there's logic to the timer. So when I take my finger off this button, this becomes false. The timer will be timing, right? So the yellow light will be on for 4 seconds. How about the done bit? Well, same as the done bit. The done bit will stay true for 4 seconds. So when I force that off, red goes out, yellow goes on, and it goes on for 4 seconds, and then they both go back to their natural state. Okay, so I think this is lab like 7 or something. This is what you need to do. You need to work yourselves through these to convince yourself on how they work. Type of stuff that I'm going to put on the exam right here. Okay, what was the other one? The other one was RTO. Okay, the RTO is the retentive timer. It's exactly like the on delay, only that it retains its time though. So because it retains its time, you need a reset bit. I'm going to, oops. All right, so this one's exactly the same as the on delay timer, with the exception it retains its time. So with the off delay timer, if we stopped it after 2 seconds, then everything just the accumulator gets driven back to 0. And the only difference with this one is the accumulator holds its value. So it's an on delay timer with a retentive feature. Okay, so when I force that on, so it starts its timing. And then when I force this off, I can see it held its value. And now when I start it again, it just picks up where it left off. And then when I force this off, remove all forces, this accumulator stays stuck at 4,000. That's what I need this reset bit for right here. Yeah, a ton would just reset when it's forced off. Yes. An on delay timer, the accumulator doesn't stay at the value. So now when I force this on, I reset the timer. So let me just okay, so I switched this back to an on delay. And the idea here is when I force that on, oops, I've got this, get rid of that. Okay, so when I force this on, then I force it off, the accumulator goes back to 0. So the TON and the RTO, same thing, with the RTO has the retentive feature. All right, I think what I'm going to do, I might save counter for tomorrow and let us go back to go back and try to get online. Okay, we've been at this a couple hours. Why don't what I'm going to do is, if you were able to get online and you had no problems, then you're good to go for tomorrow. Tomorrow in PLCs, what we're going to do is we're going to pick this up where we left off. I'm going to go over counter, and then we're going to break off into our labs. So our labs is where we're going to systematically work our way through all of this material. So it's a ton of material we looked at today, and we're going to cover it all in the labs in depth, one little piece at a time. So I'm going to stop the recording here. Okay, so what we're going to do now is I'm going to break us off into groups. If you had trouble with getting online, now is the time to fix that. And If you never had any trouble getting online, then you're free to work on whatever you want to work on. So tomorrow, what you should do for tonight is you have these tutorials right here in PLCs. Where are they here? Yeah, these tutorials right here. You can do the PLC program operation tutorial, timers counters tutorial. Yeah, tomorrow it's going to be one operator, and the idea is we're going to have new groups each time, and I would like to cycle the operators around as much as possible, so so that everybody has an opportunity to go in and try working with this. So one person's operating it, and everybody else is helping out. And I think probably groups of 6, or I think groups of 3 or 4 are too small. I think groups of 8 are too big. So somewhere around 6 or 7 is ideal. No, everybody can access the lab computers. Everybody can access the lab computers, but only one person can be on the PLC at one time. Yeah. So there's only one person who can be downloading to the PLC. Everybody could be working along with it, but the only thing is only one person can download it. So it doesn't hurt if everybody VPNs in, everybody's working their way through it, but then to actually see what's happening, only the one person who's in charge or who's running the tutorial it can download. Otherwise, you'll start kicking each other off. And we're always going to keep the same IP addresses. Group 1 is always 100. Group 2 is always 120. Group 3, 130, and so on and so forth. Yeah, 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 yeah. Multiple people can't download to the same controller. You're just going to start kicking each other off. Yeah, exactly. Okay, before I break us into the groups, is there any generic questions that might involve everybody?
But everyone can still see like the person doing the work, right?
Yeah, that's the idea. That's the idea. So whoever's in charge is sharing their screen, and then everybody else is helping out. So you have the lab open. You're working through it. You could even have the PLC program open. That's fine. Actually, you know what? That might come. You might get a conflict there because of licensing. Yeah, yeah. If multiple people open up the PLC program, then we could have licensing issues. Yeah, so it should only be the person who's demonstrating have the PLC program open. Okay, so I'm going to break us into the groups, and then I'm going to show you. You get me to come in, and I'll demonstrate what you need to do if you're not sure. Okay, so here is what you want to do. You want to VPN into our classroom, and you want to connect to our PLC. If you can do that, then you're ahead of the game, and you can just work on the tutorials. Okay, I'm going to break us into groups here.
You are currently the only person in this conference. You are now muted. You are now unmuted.
No, it was just getting in. Like, if you have troubles getting in, then one of us is supposed to try and get in to show the others how to do it, basically. Yeah.
I just have no idea where to put the address. Oh, okay. Yeah, so then how do we even get to see your screen at this point? Yeah, like I'm not really seeing a whole lot right now, and this is like the same boat I was in before. Oh, come on.
Yeah.
I got mine working.
I figured it out a little bit.
Yeah, I'm definitely this far. Yeah, but the two programs we're using, that's just like Studio 5000 and RS Logix. Is that the one? Oh, RS Links, okay. Oh, okay.
How do you share screen? No, that's fine. I was just wondering how, because I didn't see a button even before you started sharing. Right.
Ooh.
Yeah, I see it. Okay, that's what I was wondering. All right.
So we're just gonna wait for him at this point, or are we good?
I think we're just good.
I think if you can get into it, you're good. Yeah.
All right, cool. It's fucking hot. Let's get out of here.
It
Oh,
is
yeah,
well.
she's toasty.
All right, see ya.
See?
Yeah.